Okay, good news for you guys. This is the last, well, maybe good news, maybe not. This is the last thermodynamics stuff that we're going to cover for this unit. So I know we've been racing through this stuff. You're going to have some time next week to work on practice problems because we're doing a lab. So it'll slow down a little bit. Our test is not until next Friday, and this is the last new content that we're learning for this unit. So just take a breath. We'll get through this. Hopefully Hess's law made sense to you. I know last year this made a little bit less sense to students, but it's not that bad if you understand what we're talking about here, okay? You just need to understand that there is a certain delta H. It's a special delta H called the delta H of formation, okay? Enthalpy of formation. And all that means is it's the amount of heat, it's the amount of heat change, I should say, that happens anytime that you are making a compound from its elements, okay? And it's 1 mole of a compound, right? So that's the delta H formation. And these are actually useful because if we have a table of a bunch of these delta H formation, we can actually combine that with Hess's law, and we can use those for finding the delta H of an entire reaction fairly easily, okay? So this is just another strategy, really, for finding the delta H of an entire reaction, and this is a way that scientists use quite often. Here are some standard enthalpies of formation, standard heats of formation, okay? So for example here, with this acetylene, this C2H2, or actually let me do ammonia, because I think the C2H2 comes up later on in one of the sample problems. So this ammonia right here, the NH3, its delta H of formation is negative 46.19 kilojoules per mole, okay? And so what that means is the heat of formation to form NH3, we're going to need, there's some nitrogen in that compound, and nitrogen in its elemental form is N2, okay? And there's hydrogen in that compound, and hydrogen in its elemental form is H2, okay? Now, the tricky part about this is we want to form 1 mole of the of the product. Now, this isn't balanced the way that it's written right now, okay? And so to balance this, we're going to have to put a 2 here, a 3 here, and I think that does it, okay? And so actually to form 1 mole of this compound, because to form 1 mole of the NH3, we're going to have to reduce these coefficients, and that's why sometimes in thermodynamics you actually get half coefficients and stuff like that, and I know it's weird. But the way that we would actually write this as a heat of formation, it's going to be 1/2 N2 plus 3/2 H2 gives us 1 mole of NH3, okay? And all I did here is I just divided this whole, or I guess multiplied this whole thing by 1/2, okay? That way I only have 1 mole of the product instead of 2 moles, which we had when we wrote it the normal way that we write it. So with thermodynamic equations, sometimes you're going to see half coefficients like that, and it's a little bit weird, but just remember the coefficient is just telling you a mole ratio, okay? So you can put half coefficients there if you want to. We don't normally do that when we balance equations, but with thermodynamic equations, sometimes we do, okay? And so basically what we're talking about with the delta H of formation, that's the amount of heat change that would happen when we take 1/2 a mole of N2, we react it with 3/2 moles of H2, and we make 1 mole of NH3, okay? And it turns out that heat change is negative 46.19 kilojoules per mole, okay? So that's how that works. That's what an enthalpy of formation is. So a sample problem here: for which of the following reactions at 25 degrees would the enthalpy change? Oh, I need to go back and talk about that for a second also. Standard conditions, okay? So usually these heats of formation are measured at 25 degrees Celsius and 1.00 atmospheres of pressure, okay? I say usually, they always are, okay? So we have a standard set of conditions that we usually do these delta H of formations at, and that's 25 degrees Celsius, 1 atmosphere of pressure. You just need to remember that. That's what that little degrees sign there means. So don't let that throw you. This delta H, we're familiar with that. The F here just means formation, and the degree sign here just means It's at 25 degrees Celsius and 1 atmosphere of pressure. It's standard conditions. All right. So for which of the following at 25 would the enthalpy change represent a standard enthalpy of formation? Okay, again, we're assuming that we're at 1 atmosphere of pressure. They didn't say that, but let's assume that on this one. All right, so let's look at this first one here. The compound that's being formed is Na2O. So there are two elements in that compound, sodium and oxygen. Okay, and it looks like we've got sodium in its elemental form, oxygen in its elemental form because it's diatomic, and we have 1 mole of the product, right? And in order to get 1 mole of the product, we have to have a 1/2 coefficient on the O2, but that's fine. So that one, it looks like that one, the enthalpy change would be a standard heat of formation. Okay. The second one here, KCl is our compound. This is potassium in its elemental form, although, well, I mean, it's fine. It's a liquid. That's unusual for potassium. Usually it's solid form at room temperature. And then chlorine is in its gas form, diatomic, which is fine. But the problem with this one is we've got 2 moles of the product being made, okay? So here, the delta H does not equal the heat of formation, okay? We would have to change this thing so that this was a 1 coefficient, this is a 1/2, and this is a 1. Okay, and if we did that, then it would represent a heat of formation. But right now, this delta H is going to be twice as big as the heat of formation. And then the last one here, oh gosh, that's not the heat of formation at all, right? Because it's not, we're not even forming 1 product here, okay? So the way this one is written, the delta H for this one is not going to equate to a heat of formation at all, because it's, you know, it's not even a compound being formed from its elements. It's actually a compound breaking apart into its elements. So that one, the delta H is not going to equal the delta H of formation either. Okay. All right, now this is where this gets a little bit weird, and what I'm trying to do here is I'm trying to explain to you the rationale behind why we can use the equation that I'm about to show you, okay? So for some people this is going to help. For some people this might confuse you a little bit. Even if you get a little bit confused on this part, if you can remember the formula and know how to use it, you should be okay, all right? But I would like for you to be able to understand why we're doing this, and it sort of relates to Hess's law, okay? So let's say we've got this reaction here. We've got C3H8 plus 5O2. We're just burning the C3H8, and we're doing a combustion reaction like we normally do. Okay. Now we can think about this reaction as though it is occurring in 3 different steps. Okay. So the first step here we can think of, maybe this C3H8 is breaking apart into carbon and hydrogen. Okay. Now if you look at this, this is actually a heat of formation in reverse, right? Because in the heat of formation, we're making 1 mole of the product. So this is actually the exact opposite of a heat of formation, which actually, if I go back over here to the screen before, it looks like this one is actually a heat of formation in reverse also, because letter C here, because we're making 1 mole of the product. So actually, the delta H here is going to be exactly the opposite of the delta H of formation. Okay? So that's one reaction that's happening here. Another reaction that we can think of happening here, to make the CO2 on the product side, you've got the carbon and the oxygen coming together to form CO2. Okay? And then the third step in this reaction, to make the water, the hydrogen and the oxygen are coming together to form H2O. Okay? Now, what we might notice here is that this first one, the delta H is equal to the opposite of the delta H of formation for C3H8. So if we could actually look up the value of C3H8, its heat of formation, this delta H would be exactly the opposite of that. Okay? This one down here, this one, the delta H is actually equal to 3 times the delta H of formation. Okay? Because we're forming 3 moles of the product here from its elements. And then this one, the delta H is actually 4 times the heat of formation, because we're making 4 moles of this product from its elements, okay? And so I just wanted you to sort of understand that how these are related to their heats of formation, okay? So that when we start doing stuff to this, it's going to make sense in a minute, hopefully. What do we got here? Okay, so then when we add all of those up, if we add them all together, that's going to give us this total reaction that we started with. So we're doing a Hess's law type thing here, okay? And if we know the delta H of each of these things based on how they relate to their heat of formation, then we can actually add all of those together. So maybe I shouldn't have taken those away, but we've got so we said the delta H here is equal to the opposite of the delta H of formation, okay, on this first one. So if I look up the heat of formation for C3H8, and actually I should have that in front of me, I don't. Hang on just one second, let me look that up. You should have it on your note sheet. I believe C3H8 is one of the ones that I gave you in that chart that you have. Sorry about this, it's a waste of time. Okay, C3H8. Oh, it is not on that chart. Okay, but what it is negative 103.85, okay? So negative 103.85 is that heat of formation, okay? But the thing is, because we're doing it in reverse, it's going to be a positive 103.85, okay? So plus 103.85. And they actually have that written up there. I didn't realize that. They already have that, okay? And then our second delta H here, remember, delta H for the second one is going to equal the heat of formation times 3, okay? I should have written that down here, sorry. Okay, so we're multiplying that times 3. And the heat of formation for the CO2, now that one is on your chart, okay? That one is negative 393.5 kilojoules. So if we take negative 393.5, this delta heat of formation right here, and multiply it times 3, that gives us the negative 1181 that we have there, okay? And then this last one here, this delta H is going to equal 4 times the heat of formation, which the heat of formation for water as a liquid is negative 285.8. Okay, so we multiply negative 285.8 times 3, that's going to give us a negative 1143. Okay, so then when we add all of those together, our overall delta H for the reaction is going to equal negative 2,220 kilojoules. Okay, so you kind of see how that works. What we're doing here is on this first one, this C3H8 right here, this is a reactant up in this reaction, and we're flipping the delta H, okay? We're changing it from a positive to a negative, or if it was a negative, we change it from a negative to a positive. And then anytime we have coefficients in front of either the reactants or products, we're multiplying the heat of formation by that coefficient, okay? And so here's how this equation ends up working out. Now this looks weird, but this is about the way that this is written on your equation sheet, so you kind of need to know what this means. This right here, this sigma, it means the sum, okay? So we're taking the sum of the products, the heat of formation for the products, minus the sum of the heat of formation of the reactants, okay? And then this N and M right here, that's just reminding you to multiply the heats of formation by the coefficients in the equation, okay? So let me show you how this is going to work. Well, actually, and then they basically showed you how this works. Now, the other thing that we didn't talk about is oxygen. We completely ignored oxygen when we did that last equation, and the question is, why? And the reason why is because the heat of formation of any element in its elemental form is 0, okay? So this oxygen right here its heat of formation, because it's in its natural state, its elemental form, it's going to be 0. Okay, so we almost don't really even need to take it into account. So then to calculate the delta H for this one, what we're going to do here is we're going to take the sum of the products. Okay, these are the products right here. This is the CO2, the heat of formation for the CO2, and this is the heat of formation for the H2O. We multiplied that by 3 and by 4 because those are the coefficients in the equation. And then we're subtracting the reactants from that, okay? And there's a coefficient 1 there, so we're just multiplying this one by 1. This is the heat of formation for the C3H8, okay? And then, again, 0, that's the heat of formation for the oxygen. And we multiply that times 5, but 5 times 0 is just 5, okay? So that's how that works. That's how we calculate that. And that's going to give us the correct answer eventually. Come on. Okay. So actually the correct answer ends up being right here, negative 2,220 kilojoules. Alright, so let's do a sample problem here. Calculate the standard enthalpy change for the combustion of 1 mole of benzene. And I'm giving you all the heats of formation for the things in this reaction, okay? When we combust something, we need to write an equation here. This is going to be C6H6 plus O2, and that's going to give us CO2 plus H2O. Okay, now it's important that we know the coefficients in this chemical reaction because that's going to tell us what to multiply by when we calculate our heats of formation. So on this one, let's see if I put a 6 here. And I'm going to have to put a 2 here, it looks like. So that's going to be 12, so I put a 6 here. And I'm going to have to put a 12 here. And that gives me 24, 30, so then I put a 15 here. So that's fun. Okay, so we've got some big coefficients here, so that's going to be kind of messy. But what we're going to do here is we're going to take the heats of formation of each of our products, CO2 and H2O, and we're going to subtract the heats of formation of our reactants. Okay, so the heat of formation for the CO2, again, is negative 393.5 kilojoules. And then we multiply that by 2 because there's a coefficient 2. Oh, I'm sorry. What am I doing? We multiply that by 12 because there's a coefficient 12 in front of the CO2. And then we're going to add that to the H2O, which the H2O in this one is also a liquid. Okay, you have to pay attention to the state of matter because the heat of formation of H2O liquid is different than the heat of formation for H2O gas. But it's negative 285.8 kilojoules, and we're going to multiply that by 6 because there's 6 moles of that. Okay, so that's the product side of this thing. Then we're going to subtract the reactant side, and the C6H6 is 49.0 kilojoules per mole on this one. Okay, so 49.0 kilojoules, and we're going to multiply that times 2. I'm being a little sloppy with my units here, in case you guys didn't notice. These all should be kilojoules per mole. And then we're multiplying this by 12 moles, and then this one should be kilojoules per mole, and we're multiplying it by 6 moles. This one should be kilojoules per mole, and we're multiplying it by 2 moles. Okay. And then I just completely ignored the oxygen again. But the reason for that is it's an element. It's diatomic. So in its elemental form, it's 0. Okay, its heat of formation is 0, so we don't have to worry about it. So then when we work all this out, when we do all of this here, we should end up with negative 3267 kilojoules as the heat of combustion for this reaction. Okay. Oh, I take it back. I apologize. That's the heat of, sorry, that is the right answer because I'm looking in the book for that, negative 3267. But it's asking us for the heat of combustion of 1 mole of benzene, okay? So when we balanced this equation, we really should have used fractional coefficients. So this one should have been 1, this one should have been 15 over 2, this one should have been 6, and this one should have been 3, okay? So that would actually cut our entire answer in half, okay? Our heat of combustion here should be half as much. So it's going to be negative 3267. If you worked out this number the way that we did it, you would get twice that. You get negative 6534, okay? But if you had the coefficients the correct way, because we're combusting 1 mole of benzene here. Now, what you could do here, you could say, after you figure this out, okay, this is negative 64 kilojoules per every 2 moles of benzene, because that's what we found here since we have the 2 coefficient in front of the C6H6. Just divide that by 2, and that's going to give us our answer down here. Okay. All right. And then the next part of this problem, come on. What's going on? Sorry, we locked up there for a second. Okay, compare the quantity of heat produced by combustion of 1 gram of propane to that produced by 1 gram of benzene. All right, so on this one, well, see, they're going back to an example from earlier in the book, okay? And the example that they did earlier in the book, and we won't go through this, but the delta H for the combustion of propane is negative 2,220 kilojoules per mole. And we just found that the delta H for the combustion of benzene was negative 3267 kilojoules per mole. Okay. Now what they're asking us for is to compare the heat produced by the combustion of 1 gram of propane to that produced by 1 gram of benzene. Okay, this is propane here, and this is benzene. So we have it in kilojoules per mole right now. So what I would do is just do some dimensional analysis on this. 1.0 grams of propane. Actually, we did calculate this one. This is a C3H8. Now, again, I wouldn't expect you to know that yet either, because we haven't talked about how to name organic compounds. Grams of C3H8 over moles, and that's about 644. Yeah. I wasn't just talking to myself. There's someone in here. In case you guys think I'm weird. 0.0227. I'm not sure why I did that. Hang on. Sorry. Because we got one more step here. You could do it that way, but let's just go ahead and finish this. So, in every mole of propane, we're making a certain amount of kilojoules here. It's negative 2,220 kilojoules per 1 mole of propane. So that'll tell us the heat given off by 1 gram of propane burning. And then we can compare that to 1.0 gram of benzene, which is C6H6. And in 1 mole of that, that's 78 grams. 3267 kilojoules and 1 mole of that. Okay. So then when we work all this out, negative 50.5 kilojoules being made here, or being given off, I guess I should say, because it's an exothermic reaction. and negative 41.9 kilojoules here. That might surprise you a little bit because the kilojoules per mole is higher for the benzene than it is for the propane, but because the molar mass of the benzene is higher than the propane, having 1 gram of each of those, it's actually, the propane is going to give off more energy for 1 gram of propane than the benzene. Okay, this really isn't working. Okay, one more sample problem here and then we're done. And this is, very similar to what we've already done. This time they're actually giving you the chemical formula, which is nice. This is just a little backwards from what we've done. They're telling us the standard enthalpy change for this reaction, okay? So they're telling us the delta H for this reaction right here at standard conditions is 178.1. Which, again, just thinking about what that tells us that this is an endothermic reaction because it's a positive delta H. Okay. Now what they want us to do is use the standard enthalpies of formation of CaO and CO2 and calculate the standard enthalpy of formation of CaCO3. Okay. And so these are our products right here. We're going to do products minus reactants, and we've got to look up some values here. You should have these values on your table. In the notes. Yeah, they're all in there. And actually the CaCO3 is in there too, so you can double check at the end and make sure that we got this right. But this time we know the answer, the punchline. So 178.1 kilojoules is equal to, and then we're going to set up our products minus reactants here that we've been doing. Okay, so CaO, we've got 1 mole of that, and the heat of formation for the calcium oxide is negative 635.5. So negative 635.5. And there's only 1 mole of that, so we're multiplying that by 1. Okay, and then we're adding that to the CO2, which the heat of formation for CO2 again is negative 393.5. And then we're multiplying that also by 1. Okay, and that is our product side. And we're going to subtract the reactant side from that, but that's the one that we don't know. Okay, that's our X, that's what they're wanting us to find. Even though you can look that up in that chart and it will tell you exactly what it is. We want to see if we can work backwards and find it this way. Okay, so then once you figure all that out, you're going to get, let's see, on the, and maybe I should write this all out here so that you can see what's going on here. 178.1 kilojoules should be equal to, when you add all of this together, you should get negative 1029 minus X. Okay, and then when you add the 1029 to both sides, $1207.1 equals negative X. Okay, and you have to be careful there. You still got your negative sign on this X. So then our X here actually ends up being negative 1207.1 kilojoules. And then if you want to come and check that in the book, on your chart, that's exactly what it is, negative 1207.1. Okay, so this time, again, we're just solving for something that's in the equation instead of figuring out the overall heat of the reaction that's happening. They're giving you the heat of the reaction. They're asking for one of the heats of formation. Okay? All right, so that is it for thermochemistry. We're going to do a lot of practice on this in class on Monday, and then we'll do a lab Tuesday, Wednesday. We'll review Thursday, and then test Friday. So that's the plan. All right, see you guys next time, or see you guys in class.